Hi everyone, and welcome to Semester B in Physical Science. Today our flipped recording is over Lesson 1.1, Work and Machines. So just a couple of reminders as you get started. Be sure to take notes during the recording. You can use the unit note guide or your own notes by hand or typing. Just be sure to title your note page with the lesson number and the title. So 1.1, Work and Machines. And then we will go ahead and jump in. So reminder, go into when you're going to complete a lesson. Don't use My Schedule. Just log into your course and click Content. And from there, hopefully as you're getting started, you've seen the video on how to work in the course. And you've downloaded the note-taking guide. That way you can take notes as you work through. And then today we're starting in 1.01, so Work and Machines. All right, so you'll notice if you look back here, you see this note-taking guide in 1.01. There's some instructions. If you log into 1.01 and you go from My Schedule, it immediately takes you here. So you're missing some information. That's why it's so important. So with that, let's jump in. Always 1.01, the first lesson in each unit is going to be an overview. It's going to give you a lot of information and kind of go over everything in the unit. So you don't have to memorize and learn every single thing in the very first lesson because there is always a lot. So if we take a look, we're talking about forces acting on objects. We know changes occur. So think about applying a force to a baseball by throwing it to a friend. What changes occur? Not only does the object's momentum change, but so does its energy. So in this module, we will explore how force relates to energy through work. And you'll also examine how work can be made easier using machines. You live in a world full of energy, so it's time for you to explore and see all the ways work and machines are involved in your daily life. All right, so in this section you have a student guide that's a PDF. Sometimes they're helpful and sometimes they are not. These things are not required for you to submit for grading, so you do not have to spend the extra time there. Okay, and as we go through vocabulary, I do encourage you to put the vocabulary down. It says during this module you'll encounter 20 words. Those are always going to be the Part 2 test. Questions is some vocab matching. So here's a list. You've also got a graphic organizer. Again, not required to be submitted, but you will want the vocabulary words in your notes for the Part 2 test. And then this is just more information on the graphic organizer. Again, you do not submit that for grading. So we'll go through these pages really quick. Now we're into read, which is getting us started into talking about work. And so to work might mean household chores, school assignments, or different types of jobs, like carrying a large load of firewood from your backyard into your house. Or if you're struggling to hold up heavy wood, it may seem like a lot of work. But according to a scientific meaning of work, if the activity does not require work, this activity, you're holding logs in your hand and you're not moving, they're just holding, staying there. So there's a definition of work, and if the object doesn't move, it's saying work is not being done. So how can this be? So in the lesson, we're going to take a look and make sure we understand what work means. All right, so as we get into work, in a scientific term, a force exerted on an object does work. So if you like to take notes as you go along and fill out your definitions as you come across them, you'll go ahead and put this in your notes. Using an applied force to make an object move You may want to circle the word move because that is the key to work. So when the object moves a distance in the direction of the force. And so you do work by using an applied force to move an object. When the force does work on the object moves in the same direction as the force. For example, when you lift a pile of books from the floor, work is being done. Your arms exert an upward force on the books that move them up and off the floor. However, if you carry those books across the room, your arms are not doing work. But isn't the force exerted by your arms still keeping the books up in the air? Yes, but since the books are now moving forward as you walk, and the motion and the force are not in the same direction, work is not being done by your arms. So work depends on force and distance. Imagine that you're trying to move a bookshelf filled with books. You push with all your might against the bookshelf, but it doesn't move. Did the force you exerted do any work? So even if a great amount of force is applied to an object, it may not always do work. You may feel tired from trying to push the bookshelf, but since it did not move, no work was done. Work involves both force and motion in the same direction. So that sentence is a really good thing to have in your notes. And the equation, work equals force times distance. I would put it both of these ways with the letters as well as the actual spelled out. So you know that F is force and D is distance. All right, so also it's important to put down a practice problem in your notes so you can understand how you worked it out. So imagine that there's a solid iron block resting on the floor next to a table. It weighs 10 newtons, which is about 2.25 pounds. Homer Jones, a physics student, sees the block on the floor and decides to place it on the table, which is 1 meter high. He lifts the block up 1 meter and places it on the table. Homer's muscles used chemical energy to exert a force over a distance and perform work on the iron block. But how much work? So you're going to apply the equation work equals force times distance to determine how much work was done. So you can select the animation here to see how we solve the problem. You can see that he's picking it up. It's very tiny here. And so you're seeing just picking up the block. So notice the units for work are Newton meters. That's also something helpful to have in your notes. A Newton meter is the force of 1 Newton applied over the distance of 1 meter. So if we remember, James Watt is the Scottish inventor and engineer who worked at improving and modifying the early steam engine. This improved the steam engine. It proved to be the key to innovation that helped usher in the Industrial Revolution. So many years after his death, the British Association gave his name the unit of electrical power. So if you remember Watt, it's the unit of electrical power. All right, so going on, the joule. This is another unit of measurement. So in the previous example, work was expressed in the units of Newton meters, which is a Newton times a meter. 1 Newton meter is equivalent to 1 joule. So the SI unit of work or energy. So you definitely want to have this in your notes. Sometimes it gets confusing for trying to figure out the unit of measurement that you're going to be using for all of these different terms. So I encourage you to put the unit of measurement in there as well. So write out the word joule, write out the SI unit for measuring it. For work is a Newton meter or a joule. All right, so from there, we saw that Homer did 10 joules of work to lift the iron block onto the table. So you can watch the animation to help you understand this concept. So we watched it before. It's very small, a little bit difficult. So energy is the ability to do work, and each joule of work corresponds to a joule of energy. So this is something else, a definition of energy, the ability to do work. So that definition needs to go in your notes as well. And because energy is required to do work, you might also say that Homer used 10 joules of energy to lift the block. So keep it simple. This is just a recap. You may recall that 1 Newton is equivalent to 1 kilogram, and then this is kilogram meters per second squared, and this comes from multiplying the mass times acceleration. Therefore, 1 Newton meter, which is 1 joule, is actually equivalent to 1 kilogram meters per second, meters squared per second squared. So if you look at that. So it's a lot easier to express these units by just saying a joule instead of this other complex unit. All right. So we're moving on to the next page. Seems like I skipped a page. I don't think so. Okay. And you might hear my dog snoring in the background. All right, so practice problems. We're going to put one of these in your notes because you'll definitely want to see how you worked it out when you are taking a quiz or a test. So try these 2 work-related problems. The first thing you always need to do is identify what you need to know from the problem. So what you know and what you don't know. So then you'll solve for that. And remember that work is done by a force and when the force is applied over a distance. So mathematically, this is expressed by using the equation work equals force times distance. So problem 1 says your friend has a job as a pizza delivery person. She carries a few pizzas weighing 20 newtons up 4 flights of stairs, a height of 30 meters. How much work did she do? So remember, we've got some numbers here, and we are trying to find how much work she did. Right? So we have a force, 20 newtons, distance, 30 meters. So we'd multiply those. That is so tiny, I'm not sure how anyone can see it, but we use this formula, force times distance. So again, 20 times 30. All right, so that should have given you 60. I don't even know if you can see that that's there. And you can also always click this text version and it'll open a Word document to tell you everything that is here, which is silly that it's that tiny. So going on to question 2, another friend of yours who's taking an earth science class tries to move a rock with a weight of 10,000 newtons. He strains and huffs and puffs and sweats, but he fails to budge the rock. How much work did your friend do? So you may be questioning here, work times distance. I don't see another number. I just see the actually the force. So what do? Remember, if that doesn't move, that means the distance is 0. So that would mean no work is done. All right, we're moving on. Work and time. So far, you've established that lifting a 10 Newton block over a distance of 1 meter requires 10 joules of work. Would this quantity change if the block were lifted more quickly or more slowly? So in other words, does the time it takes to complete the work affect the amount of work required? So watch the animation to see the relationship between work and time. Notice that no matter whether it takes 2, 10, or 50 seconds, the amount of work does not change. So you may want to put something in your notes that just says time does not affect the amount of work done. And we can see it's not a part of the equation, right? So not a factor. So how can this be? If you look again at how we determine work, force times distance, it doesn't say anything here about time. So there's only 2 factors involved. Therefore, time does not affect the amount of work required. So that might be noteworthy for you as well. All right, now we're talking about something new. This is called power. Time is a factor when you're calculating power. Power is the rate at which work is done. So in scientific terms, power is the rate at which work is done. Another definition for you. So power measures how fast work happens or how quickly energy is used. And it can be calculated using this equation. So remember, you want this formula as well. Power equals work divided by time. Suppose a man wants to cut down a tree. He can use either a handsaw or a chainsaw. No matter which he uses, though, it will require the same amount of work to cut the tree down. However, he can cut the tree down much faster with the chainsaw rather than a handsaw. Therefore, a chainsaw has more power, which is how we have learned to come and call these things power tools, right? So all else being equal, faster work means more power and slower work means less power. All right, so the watt. Since power is determined by dividing work in joules by time in seconds, the units for power can be expressed as joules per second. However, to simplify this unit, power is measured in the SI unit of watts. That's a capital W. So 1 watt is equal to 1 joule per second. And I would write all of those things out. So you know that power is measured in watts. That symbol is a capital W. You need to write that down. And that 1 watt equals 1 joule per second. So notice that the symbol for watt is a capital W, which is similar for work, which is also a capital W. If you look at the font, though, they're a little bit different. Both symbols are an uppercase W, but the symbol for work is italicized. Make sure you know the difference in those two things. So you may want to write out the word work and italicize your W, and then watt, and leave it normal and just circle the difference there. And then make sure you don't confuse those when you are working on different equations. So now we're calculating power. So if we look at an example here, Homer Jones and the iron block. Now you can calculate the power involved in lifting the 10 Newton block to a height of 1 meter in 2 seconds. So 10 seconds and then 50 seconds. So if the work of lifting the block is completed in 2 seconds, power is calculated as follows. So work would be 10 joules over 2 seconds, which equals 5 watts. So you may want to put that example in your notes as well. All right, moving on, power and energy. Power is defined at which the rate work is done. Since work requires energy, power can also be defined as the rate at which energy is used. So that would be a good sentence to include in your notes as well. And you can apply this information using the formula P equals W over T. So that's work over time when you're solving a problem. So suppose you have a light bulb that uses 100 joules of energy per second. What is the light bulb's power rating? So P equals work over time. That would give you 100 joules divided by 1 second, which equals a 100 watt bulb. So the light bulb has a power rating of 100 watts. So you can try doing another problem like that, and just practice doing those math calculations. All right, so here is a great way to make sure that you understand these different concepts we've talked about in the lesson. Is just pushing a box across the floor. Is the item moving? Then you could put, yes, work is being done. You run up the stairs in 3 seconds. Remember, power is requiring like work and time. So you're going up the stairs. Is that power? It's giving us time. We could put it there. You lift the box from the floor to the table. So it's moving. We have a distance. It takes you 10 minutes to climb a hill. So we have this. And then you can hang on tight to a rope with your with your feet off the ground. So we are not moving. You're hanging on to the rope. So really no work is being done. Carry your books across the room. It says your force, doesn't let me scroll down there. Your force is upwards. So remember we read that earlier. No work is being done. You do 20 push-ups in a minute while your friend only does 10. 20 push-ups in 1 minute. So you're able to calculate power. You sweep the floor using a push broom. So the broom is moving. And then you push hard on a boulder, but it won't budge. No work is being done. Let's check those. So we got all of those correct. And then we're just going over and talking through the simple machines that we'll be covering in more detail. So for time's sake, we won't go through all of those. You definitely want to have them listed out, but you will cover those in another lesson. So with that, let's wrap up today. Make sure your notes are complete. Check your schedule for our flip follow-up session in science, and then attend Help Labs if you need any extra help. So thanks for watching and have a great day.